Okay, so this is back in our 5.1 notes, and yesterday we left off this portion about differentiating natural log of absolute value of u. So again, 5.1 notes. You can pause this as needed to get to the spot that you need to be. So we know from yesterday if we have d by du of natural log of just regular u, that equals 1 over u times u prime, or du dx, however you want to write that. So now we got to go back to our definition of absolute value and split it apart. So absolute value of u equals u sometimes and negative u some other times. It equals u if u is greater than or equal to 0. It equals negative u if u is less than 0. So then that splits us into two scenarios. Let's assume, first of all, that u is greater than 0. The equal to 0 doesn't really apply here because if I'm taking the natural log, I can't take natural log of 0 anyway. So yes, that's the definition of absolute value of u, but since I'm applying it to a natural log function, I'm not going to think about u being 0 itself because natural log of 0 doesn't make sense. So case 1 is assuming that u is greater than 0 and then working our way through. So that would mean that natural log of absolute value of u would really be the same thing as natural log of u, because if u is already positive, remember, we made that assumption. So if u is already positive, then the absolute values don't make any difference, in which case d by du, and never mind, that's got to be of something, d by du of natural log absolute value of u is equal to d by du of natural log of u just on its own or with parentheses, which is equal to 1 over u times u prime. So that's the exact same as the regular definition, because if u is already positive, then the absolute values really didn't matter. But our second scenario would be to assume that u is less than 0, so it's negative. So then natural log of absolute value of u is really the same thing as, coming back up here to our definition. So if u is already less than 0, then absolute value of u is the same thing as negative u. So that means that this is equal to natural log of negative u. And so then d by du of natural log absolute value of u is equal to d by du of natural log of negative u, which is equal to 1 over negative u times, well, if I do the chain rule is also going to incorporate this negative, so negative u prime. Well, then mathematically, I have a double negative, so that's equal to 1 over u times u prime, which is the same thing I got even if u was already positive. So again, kind of looking back through there, if u is less than 0, then the absolute value of u is equivalent to negative u. And we did those splits into different pieces a lot last chapter, actually 2 units ago, but the beginning part of chapter 4, we talked about how you split that apart. So then again, that means I'm differentiating the natural log of negative u. To differentiate natural log of anything, you do 1 over that thing times chain rule of that thing. So derivative of negative u is negative u prime. But if I have a double negative, then that cancels out. And so I'm getting the exact same thing, look here and here, even though I assumed two different things about the u. I went through both cases where u was positive and where u was negative. So I have proven that this is true. It turns out that when I take the derivative of natural log of absolute value of u, that it's the exact same derivative I get as when I take the natural log of regular u. Doesn't happen very often. Usually absolute values make a difference, but in this case it doesn't for derivatives. For the graphs of the functions, they will look different. Okay, next part. So we did these examples in notes, just I didn't like third and fourth block kind of stopped in some different places, and so I didn't pull any one certain slide. So you all haven't gotten to number 8 yet because we skipped it, so let's go there. Okay, so then here's my original function, but I take a look and see, hey, this is in absolute values, which should make me think more about splitting it apart and having more to do. But remember, we just showed that d by dx of natural log of absolute value of x is still just 1 over x. Or if I do the better definition where chain rule would be involved, if I put the u in there, then natural log of absolute value of u would be 1 over u times u prime for your chain rule. And I'd have to swap this out to be d by du as well. Okay, so then that means I'm ready to go straight to the f prime. This thing is just not changing colors very well. Okay, I'm going to go straight to f prime of x equals 1 over, and I get to drop the absolute values. They're not part of my derivative. So 1 over sine of 2x, and then I just need to do chain rule on sine of 2x. Make sure you recognize that's actually a double chain rule. So derivative of sine is cosine. So that's one chain portion. But then derivative of 2x is 2. So if you want to go back and kind of color code that, I had the issue about sine. So I took its derivative and got cosine. And then I also had the interior portion of 2x. So I took its derivative and got 2. Okay, then going back and just cleaning up. How do you think they're going to write that for a final answer? So you'd have 2 cosine of 2x on top and sine of 2x on bottom. Maybe they'll leave it that way, but I'd say they're pretty likely to say 2 times cotangent of 2x. Okay. So just going through and realizing that it doesn't make a difference for derivatives if I'm differentiating natural log of x or if I'm differentiating natural log of absolute value of x. What does make a difference is if you take a look at graphs, and so if you want to add this in any portion of your notes where you have some space, if you were to take a look at y equals natural log of x, we took a look at that. You have a vertical asymptote at 0. It goes through the point 1, 0, and it curves up roughly like this. And then if you want to compare the graph of y equals natural log of absolute value of x, there are a couple ways you can think through it. I mean, you can split this apart and graph it that way. So thinking about that this would really be a piecewise function. Oops, that's a terrible job of mixing my letters. There we go. You could think about this as piecewise natural log of x sometimes and natural log of negative x. Some other times it'd be natural log of x when x is greater than 0 and natural log of negative x when x is less than 0. And I'm leaving 0 out because I can't ever take natural log of 0. And then this would be, oops, this would be remembering that if you switch out all your x's for negative x's, that's a reflection over the y-axis. So that's one way to think about it. You have your original part that you're already used to, natural log of x, going through like this. And then you have your portion about switching over the y-axis, reflecting over the y-axis. So that would go through -1, 0, and then curve like this. That's one way to think about it. The other way to think about it would be for y equals natural log of absolute value of x. Because this is in absolute values, you know that like x equals 1 and -1 would have to behave the same. X equals 2 and -2 would have to behave the same. And so from just thinking through that way, you could think about that it's a reflection. Reflect y equals natural log of x over the y-axis and keep both parts. So that's another way of thinking through why you would get this image. You would get the same image regardless, but it's another way to think about it. Some other things you might just want to know about just remembering transformations in general. So actually I'm going to go back up here. So if this is natural log of x, and then they ask you to graph y equals natural log of x plus 2, that's a shift left by 2. So now your VA is over here at -2. Now instead of going through 1, 0, it goes through -1, 0. And that gives kids a lot of trouble sometimes because they think, oh, I can't have a negative at all with natural log. But if you plug in -1, -1 plus 2 is still positive. Get you to +1, so it behaves exactly like +1 did over here on the original. So just remembering all of your algebra techniques about how you split apart absolute values, how you do reflections, how you shift left and right, all that stuff is beneficial. Okay. The other thing that wasn't finished up on these notes was at the very end. I wanted to just go through, this comes up quite a bit if you have like maxes, mins, inflection points, things like that, if you have sign chart values. So say that you are trying to figure out max, min, relative max, min, and you come up with a critical number of x equals e to the, I don't know, 1/2, because you have to square root it or something. So then you put e to the 1/2 here. But say you, I mean, you have no idea what that is as a decimal necessarily. So you can't just eyeball it and guess. And a good choice, a safe choice would be to pick 0. But you also can't pick 0 if y has something to do with natural log of x and then some other stuff. Then you can't pick 0. You'd have to again remember how we kind of talked in earlier units about domain and think through that. So then some good choices would be, well, what's smaller than e to the 1/2? Looking at a smaller power, so like e to the 4th. And what's bigger than e to the 1/2 would be like e to the 1. And that's not that bad, even though you don't know what those are either, because if you go to plug in natural log of e to the 1/4 and then some other stuff, that part cancels and gives you 1/4. Or maybe say a better estimation would be that maybe like y prime equals natural log of x or something like that. Okay. Just remembering some strategies that if you have to plug in stuff with ease and you're without a calculator and you're like, I have no idea what this actually equals, you don't have to, because you can use exponent rules for how natural logs work and they can help you out. Okay. All right, that shows up in 5.1 homework, 5.2, it just keeps showing up because whenever we tend to do relative max, min, and inflection points with ease and natural logs, we tend to get some not nice values once we do our algebra and solve. Okay, that finishes up the little bits of 5.1 that we hadn't done.